All right, so lecture 30, we only have one more after this and then our review lecture. So this one's kind of a cleanup, all around the subject of functions. A lot of these things, they don't kind of constitute a full lecture. So unfortunately, it's a bit of a grab bag. There's a lot of small things here that might seem a little unrelated, but I've tried to collect the things that are functioning or function related. So hopefully that helps it tie together a little bit in your brain. Probably the most interesting one, I think, is lambda functions, which are a derivative of this thing functors, which we've talked about. So there's a few interesting patterns, kind of one of our last big new patterns for the semester that is worth just recognizing. And even if you don't memorize all of it, it just shows you some of the, a couple more interesting ways that C++ can masquerade itself to do interesting things. Same announcements as the last time. So we'll have a lab today that's just using these lambda functions. Real easy. It's really just writing a couple math functions, but we'll use this new thing called a lambda, which is an idea that exists in a lot of languages. Essentially, lambdas are quick throwaway functions, and sometimes they only exist long enough to fill out some argument in a function call. So they can be a little bit hard to read sometimes, but once you know what they're doing, and even when you see them in other languages, you're like, oh, that's a lambda function. So hopefully you kind of walk away with that understanding. We have our multi-threaded homework out there. Quiz 8 is available if you want to take a look at that. And I think we covered this adjustments to homework bonus stuff last time. So practice final, a couple of reminders about how we do that. That'll be available the Friday at noon before the final exam. And you'll have one try. It's ungraded, so no pressure. It's timed, but you'll still get to see the questions. They don't go away, but there will be no corrected answers this time. So you're more than welcome to review and still take your unused past quizzes. So, but if you want to kind of cut to the chase, as they say, just look at your practice exam and it'll kind of let you know what's coming. Final exam will be Tuesday at 5:40, and I'll have the corrected answers out at that following Friday at noon. Okay, so and then it's going to take me a while to grade because there's more essay to this than before. So bear with me as I try to make my way through all that stuff, and I'll give you some more details on that on Tuesday when we come into we're in the last week of everything. So today, grab bag around functions. We'll just review a couple things that I'm sure everybody knows, but it's helpful to just go over them one more time. We'll remind ourselves what functors are. We had a brief introduction to functors. Functors are like little mini classes that masquerade as functions. And we, of course, do that by overloading the parenthesis operator. So it really is just an overloaded class symbol, but it sort of behaves like a function. So we'll remind ourselves what that actually is. We'll take a look at function pointers again. I think we looked at them once, but we'll look at them again because they're super powerful. And it's one of those corners of C++ that escaped me for a while. It was like I always knew they were out there, but always, never really found a great example. So we'll kind of go over those one more time so they kind of stick with you. And then we'll dive into the last third of our lecture, which is about this thing called lambdas, which are kind of nice to do. When people do them, they feel super powerful, I guess. It could be a good interview question, I suppose. If you're taking a C++ job, somebody might be like, hey, write me a lambda that does, adds two numbers together. So we'll certainly be doing that today to get you ready for that kind of stuff. Real quick reviews. I think everybody knows this stuff, but we've been looking at prototypes for a while now. So if it's just a function and it's prototyped, you're going to see it look like that. And that can be a little striking. If you haven't been looking at C++ in a while, you might think, what is that? Oh, well, that's just a prototype. We're telling the compiler, we're promising that eventually we're going to write all of that, right? So of course, eventually we have to have those curly braces there so the compiler knows what we're going to do. So, and that very much matches methods .h files, constructors. We saw that many times doing out of class implementations of our methods in our constructors. So we won't take you through all that stuff, but I think everybody's seen that. The difference between overloading and overriding. Overloading is when we are using the same name of a function with a different function signature. And the function signature primarily comes from the argument list, not the return value. So we have to have a different function signature in order to do the overloading. And so this one here would not be legal in C++ because the only difference between the greeting above and the Boolean greeting is the return value. So we're not allowed to kind of go with something that minimal. So that just makes it easier for us to design things that don't clog up the namespace of our code. So we can all kind of, our brains can relax a little bit more. Okay, so that is our overloading. We saw that quite a while ago. Remember, our default arguments are good for anything that looks like a function or a constructor. They just give us more flexibility for how other people can use our method or our function or our constructor. So they're always nice to do. And if you're creating an array of instances of a class, then you absolutely have to have default arguments or a default constructor, because the array cannot construct itself. There's nothing there to tell it how to create an instance of a class unless the class itself has a default constructor, and that can very often rely on just having default arguments. Okay, so always good to have. Don't know if we covered inline, but if you run across it in your travels, it is kind of an interesting concept, and it used to be more popular than it is. So inline reminds or tells the compiler, hey, instead of calling the function over and over again, if it's a really small function, just copy and paste the actual code from the function right here. So in other words, if I define my function as an inline function, and then later on I say printline Jeff, it's going to replace printline Jeff with cout less than Jeff. So it's a really quick way to kind of create what used to be called a macro. And so the compiler nowadays will look at that inline and go, is that a big function or a small function? Looks small enough, I think it's probably better to just copy and paste that thing directly into everywhere it's called. And that will run faster, right? So the idea is inlining something makes it run faster, but it copies a lot of code, kind of like templating. And so it can make your code bigger, okay? So that right there would end up being replaced with that code. And if I called printline 1,000 times, then maybe I would have a bigger executable at the end. We'd have more zeros and ones in our executable binary. So there's trade-offs, but inline is a way to let the compiler make that decision to make things go faster. And it's not always going to happen, but the compiler will make the decision as to whether or not to take your advice or not. Okay. So that's a keyword you see thrown around a little bit. It's an optimization hint. You can think of it that way for the compiler, essentially. Now, on the topic of templates, just so we don't forget, we can templatize a function or we can templatize a class. All we're really doing is pouring in the type. And in fact, we're just copying and pasting the type in. That's really all templates are. It's just a giant copy paste thing where we're replacing the type name with whatever the type is we put in between the less than and greater than symbols. So we've seen that on vectors. We've seen it on all of our containers. We've seen it on static casting functions, and of course with our shared pointers all semester long. So templates are everywhere. When they're used properly and written properly, they save us a lot of coding because we don't have to have a special library for int vectors different than a special library for doubles, for example. So it's a pretty powerful thing. Okay. And of course, we can do it in classes and in functions. Now, so for the first of our topics today, functors, we saw it briefly, but I'm kind of overstating the problem here. I know we can do this, solve this many ways, but let's imagine that we were trying to write a function to increment a variable by 1. And then we said, oh, now we need a separate function that increments a variable by 2. Well, it feels kind of silly to write those two functions. Now you might say, well, let's just pass in an argument for a second argument that would be the 1 or the 2. But I don't really want to have to do that. I want a function that only accepts one argument all the time, but I kind of am spoiled and I don't want to have to write the two functions here. So functors allow us to do this by kind of having C++ write your function for you in a different way. So instead of this, right, we want to actually just have C++ develop these things for us, okay? So when we have, and the reason we want this is if you think about us passing in a function into a thread, right? That thread needs to have maybe just one argument, or as we'll look at the for each today, maybe the for each wants a function that just takes one argument. So there's a lot of reasons why we really want something like this, but we don't have to go write all of those things. So this is a clever trick to use instances of a class to act like a function, so that when we create the instance of the class, we're essentially creating the function. So if you think about it, functions are always around once the compiler compiles our code, right? They figure out what are all the functions. Functors are not around until someone creates an instance of a class. It's almost like pouring water on one of those dehydrated sponges. So functor is an idea, and we're taking the overloaded features of the class and essentially making an instance of the class look and act like a function. And so the symbol we're overloading is that parenthesis. So when we create an instance of an object, the constructor is the way we configure the created function. So if I want a function that's incrementing something by 1, I tell the functor constructor, hey, you're going to be an increment by 1 function, or you're going to be an increment by 2 function. So each instance of the functor is kind of like a separate function. They do similar things, but they can have different configurations. Okay, so here is our increment class. It's got a private variable called inc that tells it how much it's going to increment its variable by. It's got a constructor that simply remembers what the increment for this flavor of this class is going to be, and an overload for the parenthesis operator that essentially says, I'm going to just return whatever you gave me plus whatever got set up in my constructor. So a particular instance of this thing gets created like this. I'm saying, hey, this is my inc by 2 function. It's really an instance of a class, but with the benefit of our overload, I can come in here and say, cout inc by 2 func a, right? And it's going to return, it's not going to change a, so it's not really incrementing a. It's just, in this case, returning a plus 2, right? So the plus 2 is kind of baked into the instance here, and the minus 2 is baked into this instance here. And this is us using those overloaded parentheses right over here, right? So it's not really a function at all. It's just actually an instance of a class, okay? And so that's what we call a functor. There's nothing really, there's no new syntax about it. It's just a way of using this, clever way of using this function overload to achieve a new kind of behavior. So you might think, okay, it's kind of messy, that's a lot of code to write. But when we get to lambdas, we're going to see that the lambdas are essentially built on top of these functors. So we'll kind of familiarize ourselves with this idea of this functor class. But when we go to lambdas, you can at least know what ground you're standing on, right? We're just creating an instance, then using that instance to act like a function, okay? And there's not much to it, really. We have maybe 1 or 2 or 3. Notice that, maybe there's 3 or 4 variables we want to use to customize our particular functor. Those can all get passed into the constructor. So every time we create a new version of that function by creating an instance of the class, we got to pass in the correct number of arguments. But then we can just call it with one argument, okay? So later on, we talk about lambdas. We talk about the lambda capture. The lambda capture is going to be the constructor arguments. And then the thing that we pass into our functor is the regular function argument. So I'll come back and remind you about that. But you can kind of see that. And you can kind of click into these guys here. Let's see if I can get a refresh on this thing here. This one's all written for us. Come on. There we go. So there's my class. And you can see I'm just incrementing just as if it's a normal function, right? But the function gets created inside of main, right? There's no function obviously being created up there. So that's pretty cool. Once you create it, you just think of it like a function, okay? And we could have made this, not the constructor, but the overload, a reference, right? So this could be int ampersand val to inc, and we could have literally changed a in that particular case. So all of the good things that we can do with a normal function or a method are, of course, available to us in this overloaded operator here as well. Okay, so there's quite a range of things that we can do. So let's see if we can create the decrement, if you guys have not already looked at this. So we'll have initialize an original value to 12. We'll use our decrement instance to decrement the value and assign it to final value, okay? And then we'll print out what that final value is, okay? So let's have a look, okay? And here's the hint, right? Of course, you can put the ampersand in there if you want to actually get that thing to change. Oh boy, I did it. One too many of those things. All right, bear with me while I do that one more time. Okay, all right, so let's get us down to our first practice problem. Start from current, go to my share and select control share. Okay, and we're back. Okay, so let's try this thing out. Let me jump over here. Okay, refresh. Can do it. I know I can do it. Come on. Haven't lost one yet. Usually just takes a little while. Okay, so here's our decrement. So we're gonna decrement. So we're saying, hey, dec by, that's my data member, dec by equals inc dec by. Okay, so we're recording the flavor of functor we're creating. Semicolon, that's it. Okay, operator int value, decrement the value by the dec by, right? So we're going to say return val minus dec by, right? That's my private data member. Okay. And if I want to have it change something, right? Decremented by, oh, okay. Is dec by, dec by, so decrement by 2. It's kind of a misnomer. I guess I should just call it inc because we're just adding the value that we're getting. Variable 12 decremented 10. Original value is still 12, right? So if I want to change the original value, we can play around with that ampersand there. So I'll let you guys kind of give that a try. But that is the basic idea in our functors. Okay. I don't know why I called that dec. Now, here's an interesting thing. Notice that I overloaded this here. And this is an important thing. If you make this a reference, right, and say val equals val plus dec by, that's going to work if you pass a variable into it. But what if you pass something into it that's not a variable, right? You can't change that with an ampersand. So notice I've had to write 2 flavors of this so that in main, I can do that, right? And I can do that, right? One of these is going to trigger the const value, right? And the other one is going to trigger the reference value. And a lot of times it can be confusing. You write this and you feel really good about it. And then you try to do this and it crashes. It says, hey, I can't do that because you got a reference. So it's just a matter of overloading, right? Overloading that functor a little bit so you can handle both of those situations, okay? Like that, okay? Oh, sorry, this is what I meant down here, not that. That was my constructor, right? So if I try to decrement 15, that's not going to work with this one, but it is going to print out the right value here, okay? It just can't change that 15 to something else. Okay? So that was just a little extra thing that I threw in there, okay? So if you get rid of that, you're going to have a crash, right? So the whole moral of the story is try to have both flavors covered there, okay? I think I probably pointed that out in my next observation slide, okay? So we often see that happening. Those things sort of come in twos, the reference version and the non-reference version, okay? So that's kind of it, really. They're created on the fly, and we'll see this, theme come back. We talk about the lambdas. There's a bit more logic we have to pass around, and we can do all sorts of stuff this way, right? It's really quite powerful to actually implement these things, which is pretty cool. And in fact, many of the libraries we use where we've sort of passed in a class, they create the function on the fly based on that class. So we've probably seen this pattern before and didn't realize what it was, okay? So let's park that there for a moment and just switch on over to another somewhat unrelated, other than just being functions, topic called function pointers. Love function pointers. A function name is just an address. So if I have a function here called doit, and I can call the function, but I can force the name of the function to be reinterpreted as a void star. So that basically says, just give me the address in memory where that function is sitting. So we can kind of, strip away the mask on our function and force it to tell us what its address is. So reinterpret underscore cast is kind of a modern version of forcing anything back in C days, not C++. You could change any kind of pointer around to anything else. So nowadays we have to use functions like reinterpret cast or static cast kind of to do that. So here, that's all we're really doing, just to see what it is, right? So now we talked about this before. It's like there are a lot of situations where we want to call doit, we want to pass it into the myThread constructor. So what does the myThread constructor look like? How does it describe its first argument? Because it's a pointer. Well, it's a function pointer, and functions have lots of different possibilities. This one has one integer x and it returns an integer. So how do we declare that kind of argument so that we can write functions like that, right? It's kind of like a secret language almost in the way these things are. So here it is. Return type, parenthesis, star. Notice this weird star inside of the parentheses. That's the clue. It's like, okay, I got some star and a return type, and then the function name goes in there. So really, it's the function argument name for any kind of argument you want to hold on to a function pointer. And then we have to just list out all the arguments, type 1, name 1, type 2, name 2. Okay, so something like this is a pointer to a function with no arguments that returns an integer. Okay, so that is not a function. That's a variable that holds a pointer. What kind of pointer? A pointer to a function. So it's really weird looking. It looks like a function, but it's just a variable name called myfuncvar a. Now we can grab onto any other function that matches that function signature. So if I have a function like doit that takes no arguments and returns an integer, I can steal its address and store it in this variable and even pass it around. There's a different variable with a different kind of function pointer, obviously returns a double in that case, right? This one takes an integer, returns an integer. You can kind of see the pattern. It's a weird one, but once you know it, you can kind of start doing some pretty cool things by passing around function pointers and then calling them from inside of your own functions. And that's some really powerful stuff. Okay. So remember, that's a variable. That's all that is, right? These are all variables that hold on to pointers. Okay. So let's see if we can do some examples, right? There's an integer. There's a pointer to an integer. There's a, I don't think that's a function pointer, right? That's just a pointer to an integer where we happen to put some spare parentheses around it. It's very, very easy to get confused, right? The thing that's missing is the parentheses also that have to follow that, okay? Now we have a pointer to a function, okay? Easy to leave off that second part. And there's a pointer to a function, right, etc. So you can kind of see the progression there, and you can kind of try this out a little bit if you want. But that's the secret sauce, right? Because now we can imagine a situation like this. So I like this idea about, functions that share the same function signature, walk, run, whatever. Like, so these are functions that say that cause a character to animate, and they're going to animate for a certain amount of time. So it's kind of like our worker function with our threading that we talked about. But in this case, they have the same function signature. So if we design a system like this with a whole bunch of functions that have the same function signature, we can now create a variable, and then the function that we're going to call can depend on all sorts of factors. So now my func_var has been assigned run. So now I can just pass my func_var around. Nobody really knows what it is. They know how to call it because it has to take an integer, and it is a void return function. Okay. So I can say my func_var of 10, and it's going to print out I'm walking for 10 seconds or I'm running for 10 seconds, whatever function we assign to that. Okay. And that's pretty cool, right? Because otherwise we really would not have a pattern that would allow us to sort of defer what that function pointer is. Okay. Now, so where we see a name that's actually a pointer in C++, arrays, right? So arrays are kind of like that too, right? They have their own syntax as well, so we can tell the difference, but that's essentially something we pass around as arguments, okay? And you'll notice that with arrays, it's passed by reference. Old-fashioned arrays, like we can change the array inside of a function because it's a pointer, okay? And so passing a function pointer is kind of equally powerful, okay? So let's take a look at doing something a little more advanced and sort of gratuitously pulling in our maps so we don't forget about those powerful things. So this is a map with a keyboard character trigger like jump, crouch, run, like kind of game style. And some pointer is the value portion of my map, right? So key value pairs, right? So I'm going to load this map up eventually with keyboard characters and the functions they trigger, crouch, run, kind of game style, right? So there's the key, there's the value, there's the map, okay? And so now I just need to hook this thing up. And then we have a really powerful data structure that allows us to just kind of engage arbitrary functions that carry out certain things, right? All registered in this super, super powerful map. So let's see if we can kind of pull this together. So we'll create a map of these animation functions, kind of like shown on the previous slide. And then we'll go into a loop and we'll just let the user give us a command, and we'll call the right function from the map based on the command, okay? So relatively straightforward hookup, but pretty powerful, okay? And then we'll just kind of repeat that and keep going until somebody hits X. So let's take a look at how we put this one together, okay? Okay. So I'm just going to follow my own to-dos here. There we go. All right. So we've got a whole bunch of runs. These are all symbolic, right? Nothing's actually happening. Here's our pointer to a function that receives an integer, returns nothing. And we'll start out by defaulting on the run, but we won't call it. We could do it if we want to test just to see that it works. But here's our empty animation table. Key, function pointer pair. So we're hooking this thing up, right? W for walk, R for run, I for idle, etc. Okay. And now we can simply call a function. If we wanted to test it, we could say a table of R, pass in the 5 for 5 seconds. So this is really calling the value, saying go get the value associated with R. Well, what is that value? It's the run function, because we've hooked that up to our table. Okay. So that's kind of what we're after here. It's a really cool pattern. So we'll just say, hey, give me a letter. And if it's X, of course, I'll break. Otherwise, let's get an integer that represents time. So let's see if we got a variable for this. Yeah, int time. So I'll just say, see out how long. Okay. And then we'll do that. And then we'll say cin into time. Okay. And then we will say call the function. So a table, okay, square bracket, command, right? That's our command. Is command a string or character? Character. Okay. I think this is going to work. Yeah, I think this will work. We'll have to do a character and hit enter, right? But that's going to be my function. And then I just pass in the time. How long do I want it to go? Okay. So let's just see if I got that right. Okay. So walk, followed by integer, then return. Please enter the animation followed by integer. Oh, so the integer is going to be, oh, okay. I got something messed up here. Sorry. Please enter an integer followed by cin, command break, see out how long, cin time. Should work. A table command time. What am I missing here? Ah, oh, the command should work. All right, maybe. All right. I don't think I can do it all in the same line, but let's see if I do a W4. Okay, walking for 4 seconds. Okay. Oh, yeah, okay. I didn't need to do this right here. Sorry. Okay. That's all done for me. Okay. So create an information table. Nope. Wrong one. Sorry. This was the one I wanted to get rid of. Okay. Anyway, now that I've mangled it. Anyway, you can kind of see the pattern there. Walk for 3. Walk for 3. And off we go. Yeah. Run for 5. And exit. Okay. So it's pretty cool. It would be challenging to do that another way, right? Because we're literally mapping our function calls. We could do a giant case statement and do that, I guess, right? Or a switch statement. But this is so much cleaner, okay? All because we're able to map these function pointers. So I really like that. So of course, yeah, we got to test for bad input in our map and all that regular stuff. But it's a great use of those particular capabilities. Okay. Let's move on to lambdas. So keep that in mind. We'll come back and use some more function pointers or talk about them a bit. But let's talk about this idea of a lambda. So remember, our functors are instances of a class. Okay. Now in C++, rather than having all that messy, write the class and then, call the class, they decided to add what I sometimes refer to as syntactic sugar so that the compiler does a lot of that stuff for us. So a lot of languages now have this special mini function syntax called a lambda that very much acts like the instance of a class, but it has a much more concise syntax. So we don't have to go through all of that stuff. So the compiler looks at this new syntax called the lambda and writes the functor for us, and we never really have to deal with that. But we just need to remember that there's a special way of letting the compiler know we're speaking in lambdas by starting with the auto keyword. Now I know auto has other connotations, but in the way we're going to use it, it's kind of like a trigger to tell the compiler, here comes a lambda. Okay. So, and lambdas don't support templates until the 2020 compiler, which some of you might be seeing. So you might actually run into that. But here's our lambda structure. So it's kind of like the definition of a function where we say auto, here comes a lambda. Here's the name of our function, right? And then we will talk about these individual parts over the next couple slides. So the capture clause is like the constructor arguments to our functor. It almost quite literally is. The parameters are our arguments for our overloaded method, right? And this is the return type of the overloaded method. And this is the guts of the overloaded method. So we'll kind of dig into that, but we have to put a semicolon on that thing because it really is like creating an instance of a class, which is kind of like saying, int x. So we got to put a semicolon after that thing. So let's see about the name, right? Of course, that can be anything you want. You don't have to have the name. So we'll see that we can leave the name out. And if we leave the name out, the function just calls itself and then poof goes away. So we will sometimes write functors, or sorry, lambdas that only stick around for a brief moment in time, okay? But if we do give it a name, we just call it like that, f parameters, okay? Whatever the parameters are that we want to give it. And we'll see some examples here. The capture clause, as I mentioned, is like the constructor. What arguments do we want to feed to our functor constructor so that it can bake them into the f lambda? Okay, so these are the things that will be remembered by f, and then later on we can call f and just give it the minimum number of parameters that we want. So the capture clause is a bit like something called closure in JavaScript. If anybody's ever coded in JavaScript, a closure is a way of vacuuming up a whole bunch of things in your neighborhood and sending them into the constructor of your functor. Seems kind of dangerous, and it kind of is. We'll see in a minute. But that's essentially what that is. So we're essentially allowing local variables to be captured and put in the constructor, okay? And so the way we're going to do it is just by listing them. So if you have a variable in your local scope where you're writing the lambda, you just list it out. Like, oh, I want to pass my var1 and my var2 essentially to the functor constructor. So that's what kind of goes in there. And those things become kind of like constructor arguments, okay? And we can also do something tricky. We can pass them in as a reference so that the constructor can kind of change them, which is a little bit strange, okay? But notice there's no type in there. We don't have an int or a float or a double in there. We're just saying, hey, here's a variable I'm throwing down into the constructor, okay, as an argument, okay? So the capture doesn't create any new variables. It only really vacuums up the existing ones, okay? Now, a really dangerous thing to do is just say equals there, and it's going to capture everything in the scope of this particular thing, which is very much what a closure is like in JavaScript. It's a very aggressive move. It's like I'm going to dump everything into the constructor, or I'm going to dump everything in and let the constructor change it. These are really powerful things. You probably don't want to start off with that. But we'll see some examples you can kind of think about here. But then the rest is just like a function, right? Okay, what are the arguments of my function? Int I, string s, double d, etc. Okay, so we just list the arguments. Those are the things that have to be passed in all the time. And so we could say f5, foo, 1.5, etc., like a normal function, which is pretty cool. Okay, it already knows, the function in this case f knows about everything we shoved in here when we call it down here, and we don't have to list it again. It's already baked into f lambda. Okay, capture clause never changes unless we use those ampersands on it. Okay, and then the logic block, of course, is as you might expect. This is just the logic of our code. And you get to refer to whatever variables you listed here, you can refer to inside of your logic block. It's kind of crazy. Almost think of them as private variables for your constructor, that your constructor put data members in the class itself. Okay. So in this case, I could say, I could just address the individual arguments, right? So let's say I'm just printing out those arguments as the purpose of that functor. But if I had a variable up here called int a, and I put the a in there, notice I didn't say int, I just said a. It's like I'm pouring it down the chute into the constructor for my lambda. And now I can, if I want, I can incorporate the a into the body of my lambda code. It's just another variable I can refer to. And you're probably thinking like, why didn't you just kind of put it in over there? Like, why not just declare it as an argument? The reason is because f, right? Let's say f really wants to be a 3-argument function. So adding a 4th argument would make everybody unhappy for multiple reasons. So putting it in the capture kind of bakes that 4th argument into the f, but you get the benefit of always kind of relying on having it around inside the body of your lambda. Okay, so that's a little bit of the heads up. The return type and value, it's optional. Okay, so we don't have to specify it. Okay, but if we do, it allows us to do a lot of guessing. The compiler can guess what kind of thing is going to be returned. So I could say my int equals f, you know, etc. 5 foo 1.45 or double, right? And that's going to force a cast from the int to the double, right? So double is double, f returns an int. We've all seen that before, right? But the advantage is we can also use auto. I can say, hey, you be whatever you want to be. Figure it out by looking at what f returns. So in this case, the auto is not part of the lambda. It's just saying whatever the lambda gives me, that's what I'm going to become. The compiler will look at the code at compilation time and be like, oh, that's an int. Okay, so I will put an int here. We never see it. We just use the word auto because, you know, we're kind of resting our brains a little bit, right? So that's the advantage of saying, you know, what your lambda is going to give you at the end of the day, okay? Now, if you don't specify a return, notice this arrow. So in JavaScript, these are kind of called arrow functions. So there's some kind of connection between lambdas and arrow functions in JavaScript for those who might be curious. But here, there's no return type. So we will tell the lambda what to give us, right? So in this case, the compiler is going to give us whatever we're assigning it to, and there'll be no conversion. It'll automatically match the type, okay? I'm pretty sure. Now, in this case, it's going to probably match the final type of the code. I'll have to look at how we write that. But the one thing we can no longer do is use auto, because the compiler can't figure out what we're going to get back without this return value. So these are just little details, like not super critical, but you might see that it changes your answer in your lab today. So heads up on, you know, whether you've been clear about what your return value is on your lambda. Worst case, you'll just have a type difference or some kind of a truncation error. Okay? So let's look at some actual code real quick. So we're going to say auto this lambda, empty capture, cout. Okay, so there's no, actually, no, am I missing my parentheses there? I feel like I'm missing my parentheses here. I think there should be. I could be wrong though. It's been a little bit since I did this example. But auto this lambda square brackets. I'm not pulling in anything to the constructor. I'm just printing out hi there. Okay. And so I would call this function that way. Okay. Here, we're going to pass in a single argument, so you can kind of see the pattern. It's really not too complicated. Looks a little weird, but that's our lambda. And again, auto tells the compiler, here comes a lambda function, okay? So now I can say this Mickey, right? There's another one, just some kind of simple math, okay? So notice here, we haven't declared a return type here. There's no return type on it. And so it's going to be kind of determined by the type of argument that I'm returning. 2 times an int is going to be an int. So that's what we're going to get out of that thing, okay? So the return type is missing over here, okay? So I can do that. That's okay. So let's try to do our add and subtract lambdas here before we go too much further. So we'll write 2 lambdas. They go in main, right? Because we're creating an instance of a functor, and that's something that we do and want to do in main. So we're going to put our lambdas inside of main, and we'll give them 2 arguments to add an int, a double and an int, and an int and a double, right? So let's kind of go look at that and see, oops, if we can get that working okay. Okay. So this is just an example of a negate function that returns negative of I. So you can kind of use that as a pattern to start with if you want, but we'll say copy paste, right? So we want to add. So we're going to call this thing add, and we'll say 2 arguments of type int and double. So we'll say int and then double j, okay? And we'll say return I plus j, okay? And I think we're not going to return. Are we supposed to set the type of the return? I think we're leaving it typeless. Do not specify their type, right? Okay, okay. So then we'll go to our difference, right? So we'll say difference equals, and we'll have 2 arguments of type int and double. So we'll say I minus j, okay, okay. And then we'll call these. So that's pretty easy. What was I calling it? Sub? I can call it anything I want, really. I'll call it sub. So we're not typing so much stuff. Not dub, sub. There we go. Okay. So we'll say cout, add 1, 2. Okay. Yeah. And then we'll say cout sub 4, 3. Okay. And yeah. Okay. Well, let's see if I got lucky there. Okay, there we go. Okay, so add gives me the 3, subtract gives me the 1. Okay, pretty straightforward. Okay, it's just weird that these things are living in main, but pretty cool that we can do things like negate, right? Sub of 4, 3, right? It should just work. Okay, here we go. -1. Okay. Relatively straightforward. When you don't have the capture in there, it just feels like you're writing a little function with a little extra syntax thrown in there. Okay. Any questions on that one?
Add and sub, could those be reserved?
Yes, very much so. Yeah, great question. In fact, they very likely are. So is swap. Yeah, I've been burned sometimes. So that is one of the reasons why people get so upset about using namespace std all the time, because what that does is it puts those functions at right up front and center. If you leave the using namespace std out, then there's less chance of that collision. So I know I throw it in there a lot to simplify our slides, but yeah, that's a real problem that you got to be aware of. Let's try one more. Let's do a get bigger. So we're going to do an auto lambda function, returns 2 arguments, and we won't specify the type. So let's just try that one. I forget what the gotcha is. There's always a gotcha, so sometimes I forget my own gotchas. So let's see what they are here. Okay, so here's our lambda that should return 2 arguments. So we're going to say auto, or to return the larger term, auto, get bigger, and we're going to have no capture on that, right? Sorry, get bigger. My gosh, I got to go back and help myself. Get bigger equals square brackets. And then we're going to say, we didn't say int, so we'll say int x, int y, I think. Okay. And then we will have our return. Do we say type return? Returns a larger. Yeah, we'll just lock it down. We'll just say return int. So arrow returns int. We'll say if x greater than y, return x, else turn y. And of course, you can use ternary operator if you remember what that is, right? So I think that should work. And then we will kind of try to call that thing, get bigger for 5. So float. Let's add a float there so we don't lose any precision, okay? And then we'll make sure that it's a float, okay? I think I'm following my own instructions here, okay? Expected comma, I must have missed a semicolon somewhere. If this, return this, else do that. That should be okay. There's the end of my thing. What line was that on? 34. 34. Oh, semicolon. Semicolon. There we go. 5.1. Okay. Not too complicated. Okay. So you might think, why not just write a function? Well, if you're in the middle of a really huge chunk of code and you just need this one little function and you don't want to pollute the namespace, right? Outside of the function you're in, you can create a function inside of a function. And you know it's going to be totally private just for you. And you also know that when we leave whatever function you're in, all instances go away, right? So do lambdas, right? Because they are instances. So that scope bound resource management thing comes to our rescue and gets rid of our lambdas. So like it's not hanging around. So it's kind of like I get it when I need it and then it goes away, which is pretty cool, right? So there's our get bigger. And there's our ternary version, right? So you could say, return if I is greater than D, return I, else return D. Okay. Nice way to avoid the if else. Okay. So that's pretty cool because in this case, I left out in this solution, I left out the type, right? And so this was the thing I forgot, the secret sauce. This is pretty crazy. We're returning a variable type in C++, which is pretty wild, right? It's going to return the type of whatever is bigger, right? Which is not something you can do with a normal function. So not something you need every day, but it's kind of interesting. Now let's look at this capture thing because it is weird. So it's hard to come up with a great example, but let's say I just like the value of 10, but I need a function that only accepts one argument whenever somebody wants to use it. So I'm going to bake the queue in to this lambda by passing it in by value to the constructor. And the body of my kind of lambda is going to be return q times value. Okay. So I'm sort of saying, hey, this lambda is going to multiply anything times q. Okay. So now I can just say this lambda and I should get 10 times 7 is not 70, 50, right? So that should be a 5 over there. I probably updated this and didn't update that. So, so if I change Q now, it has no effect on the lambda, okay? Because imagine we passed Q into the constructor and it got wrapped into the lambda up here. So, and it wasn't by reference, it was just a copy of the lambda that went in, and so now it's locked in, okay? So changing that Q is not going to affect, we should get the same thing. I just got to fix my comments over here. That's really terrible. Write myself a little note to come back and fix that thing, okay? Sorry about the math. Okay, so that's kind of one of the things that is maybe a little surprise about the captures is it doesn't affect it later on, okay? So let's do an add mult, right? So add mult is going to take our magic Q, multiply it times the sum of two values, okay? And we'll define a variable before the add mult to pass it in via the capture, okay? And then just print it out, prove to ourselves that it works, right? And then we can change the value, just what we just talked about there. Just try it out in real life so that we can kind of remember it, hopefully. Okay, so here is our defined integer. So we'll just call it Q, int Q equals 3. Okay, we'll pass the Q into the capture area. And so we want to multiply it times the Q. Okay, so notice I didn't say int Q because Q already exists. This is just like constructor arguments. I'm pouring it in, right? But the weird thing is now I can call it Q anywhere inside of my implementation, okay? Right, and if we change Q down here and call it again, we should get no change, right? Q equals 20, and we should not see a change in that at all, okay? Okay, what happened? Did I not return? Return Q C out. Oh, I gotta take it out of quotes. Sorry. Take it out of quotes there and take it. I don't know what I was trying to do there. Oh, I see. Right. Sorry. I'm overcomplicating it. Right. This is what I really meant to do was something like this equals, yeah, add mult. That's all I was trying to do. I just didn't follow my own instructions there. Okay. So let's pop that in. See if I got it. Okay, there we go. So no change. All right. So maybe terribly obvious, but at least we've all seen it. Okay. Okay. Let me see if I missed any key things here. Yep. I think we've got most of that stuff covered pretty well. All right. So let's take a look at maybe something maybe a little more relatable, a greeting that we lock into a lambda, right? So greeting name, this maybe is something that you can relate to a little more, right? Goodbye, Mickey, right? So our lambda can kind of have a different prefix or postfix on it. So one cool lambda might be, adding quotes to any word, right? Do you want to add double quotes, single quotes, square brackets, right? So we could specify something as part of the lambda that is the prefix and postfix, and then just call it, all like that would be pretty clever, okay? Now, if we do something like this, it's pretty wild. So here we're saying we're going to let the lambda not only return a value, but modify something in the capture, okay? You can do it. It's kind of hard to imagine a really good example of where you might need that, but I think you might have one in your lab today. So here, when we say this lambda 5, double it is going to become 10 as a result of calling that function. That's kind of trippy because there's no, double it in that line of code. But if you go back and you look at your lambda, you can see what it's doing, okay? Now, the question is, what gets returned here? Because there's no clear return statement. I think this is one of those corner cases. It's going to return the last variable in the lambda. It's kind of weird. I'm gonna have to go in and look at the code, but because clearly we want to be able to return something, but we're also changing the doublet variable as well. Okay. So just kind of summarizing though, the capture piece, the capture is something we know about when we create the functor in the first place. We sort of bind it to the function permanently. The arguments come later. We don't know what the arguments are going to be right now when we're creating the lambda. Okay. So we'll pass those things later on. Okay. So most of the time we create lambdas for helper functions, and we're going to look at that next real quick. I think we'll have just enough time to look at one or two more examples. Like for each is a algorithm function from the algorithm library that works really, really well with these lambdas. But also threads, right? So here's another way you could launch a thread. So this was one way we said we'd launch a thread in a constructor. It was kind of, really messy. But if you kind of look these things up and see something like this, you might think, what is that? Well, that's a lambda sitting in the middle of the constructor argument for this thread. We're sort of binding together a worker function with some arguments and passing it in, we're passing the lambda into the actual thread constructor. Okay. So it's a trippy little thing, but sometimes you see examples like this out there in the wild, and you look at it and don't know, what is that, an array? It's like, nope, that's a lambda, right? Somebody's creating a lambda on the fly there. Okay. So we will not be doing anything like this, but I thought I'd kind of show you that. Let's take a look at the for each. We mentioned it briefly in lecture 11. And so we have to include the algorithm library, singular. I always add an S and then I get a compiler error, algorithm. So for each loops over every member of some container, and you have to give it two iterators for the first two arguments, but the third argument is a function name that can be called with each of the members of the container, like one by one by one by one. That's why we call it for each. So that means that our function can only accept one argument at a time, but we can construct our lambda with some capture if we wanted to. Okay. So let's say we have some function, right, that takes one argument and does something, right, and doesn't return anything at all. Okay. So I can use for each this way. For each vector of values, let's assume that it has values in it. Vals begin, comma, vals end. Here's the function I want you to call on each one of those values. So we kind of saw this before. So to some degree, this is a little bit of review here. We're saying, hey, I'm giving you a function pointer, that matches the function signature that is required by for each. For each requires this exact, well, something quite like that function signature, at least. I think it might be that exact function signature. And it'll just do something, right? For each thing, it'll do something. Maybe it writes it to a file. Maybe it, puts it in a global variable or something, right? Here's another example of us doing that with some strings. So we have a vector of strings. We iterate over it with for each. Some languages have this. They have a for each built in, okay? So it's a pattern that, if we grow up with the for loop, we think, what is that strange thing? That's just something we're passing a function into that carries out some special action, okay? But we can replace that whole thing with a transient lambda. And this is really where lambdas get used, I think, is instead of like going and writing some function somewhere far away outside of main, getting it loaded in a CPP file, we just write a little mini lambda right there, okay? So let's see if we can write a lambda in there to print something, right? So it'll be a print me function kind of lambda, okay? So let's take a look at this one. I know we're rounding the corner here, so I think we're doing okay on time, okay? So we have already an existing print me function that does this, okay? So convert argtype to string. So we'll just convert this to a string. Not totally sure I know where we're going with this, but string, okay. So there's our function. We're just going to print out the string. And we're going to convert this to string, okay. Okay. And we'll push some strings in there. So this is kind of crawl, walk, run for us. Vals dot push back. Wow. Okay. Vals dot push back. Okay. Oops. Okay. 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 And now we'll say for each vals begin end print me. So we're just kind of exercising the pattern. We haven't done the lambda part yet. So this is really just a warm-up exercise here. But hopefully we can all see that this is going to be past each one of the members of this as we iterate through each of the members of that. So we should see that stuff get printed out, okay? So that requires that we have this print me function floating out here somewhere in our namespace. And it's not a terrible thing, but the next step is to replace that with a lambda. I'm pretty sure that's where we're going, okay? So this is kind of what we just saw, okay? Because we all hate having to loop through and print out vectors. So let's see if we can do that. And maybe we want to customize our print me by adding a capture to our lambda as well, okay? So assuming we've got some values, and we got this for each, we want to put the lambda right here. So notice what I've done that often confuses people so much. I've moved the parenthesis down here and lined it up with the for each, so that I got lots of space to develop the third argument. This drives people crazy, but it's like, wait, what are you doing there? Oh yeah, I'm writing functions in the entire space of the third argument. That is what we are going to do. And you see this all the time in JavaScript. And if you're working with lambdas in C++, you see it too. It's like, hey, wait, there's a that, and maybe there's even a curly brace after it. And that gets really confusing. But we want to put our lambda in there because we only want to use it one time, okay? So that pattern is the first challenge to recognizing what we're doing. We're just calling for each, and we're putting a lambda in the final category there, okay? So don't confuse that with something else. So let's see if we can actually do this. So we're going to write a lambda to sum all values in the container and modify the sum through closure. I used the C++, whoops, I used the C++ reference here, sorry. I jumped too far, go back. So closure capture, I should have called it capture. So let's take a look, okay? So we got our numbers and we want to sum them all. So we're going to replace this with a lambda. So I might need some help on this myself. So we're going to, let me try. So we're not going to give it a name. We're going to do a closure around a sum variable. Where is our sum? So we should have created a sum variable for this. It's down. Oh, print using a lambda. Okay, we're just printing here. Sorry, we're just printing. So we're just going to say, sorry guys. Tell you what. Well, we'll give it. I'm gonna bail because I kind of messed myself up so much. So where is our print? Oh, I skipped the print. Oh, Jeff. Okay. Oh, here it is. So for each begin end, see if you can try this. I just feel like I'm losing ground here. I'm gonna start my closure with nothing in it. I'm going to match the data type of whatever my vector is. So I have to go up and look at what vector I have here. And then I'm just going to print it out. Okay, so that's a handy printout for, my all values vector there. But down here below, this is the interesting one. So I've got a counter here. I'm going to do a for each and create a transient lambda, which is simply going to capture the sum and make it a reference. It's going to receive each of the I values from our for each, add it to the sum, which is a reference. And so that is going to accumulate the value for the sum. And then the lambda goes away. Okay. So that is kind of a lot. Hold on, let me see if I can figure out. There we go. There's our for each, right? And our lambda in the middle of our third, that's our third argument for our lambda. Okay. That's really kind of the more advanced thing, right? That we want to introduce to you. It's like, hey, these crazy little things are creating functors or instances in a brief second, using it to snarf up a bunch of things from the for each and modify a variable by reference. Okay, that's really where lambdas end up getting used. Very transient. They just come and they go. It's like right when you need it. And very often a little tiny piece of code, not a really elaborate thing. Because if it was, you probably need to debug it and you probably want to write it somewhere else and have it around for a while for other people to use it. Okay. But here it just sort of goes away after we're done. Okay. So that's the real big takeaway, right? So our closure, I should say capture, passes in that S or that sum with a reference that allows us to kind of accumulate a value. And that's really, really powerful. Okay. So let's try this one more pattern, and then I think we'll get you guys out of here or get you into lab. So find if is kind of like for each. We're trying to find something. Okay. So we're going to try to find the first value in some container that passes some if test. Okay. And the if test is going to be controlled by our lambda. So our lambda is a little mini function that is looking for something. And if it finds what it's looking for, it's going to probably do something like return a true, right? So if it's what you want, return true. Otherwise, return false. And it only can accept one integer, but we could try to pass in some capture as Q, right? If we want to specialize the functions. Let me see if I can cover myself here and do at least one of these things on the fly. Okay. So here's our Q. Here's us. We want to write our lambda. So I'm just going to create some space here to write the lambda. Okay. And it says write lambda for the third argument. Input an integer, return true if not. So, so our lambda, okay, is going to get a Q. Okay. So we want to return true if we find something that is equal to 3, right? So there's our capture. We're going to receive, and our vector is of type int. So we're going to receive an I, okay, like so. And then we're going to say if I is equivalent to Q, return true. Otherwise, else return false. Okay. And then we'll finish off our lambda. Okay. That's all the third argument. Okay. Okay. And then down below, if we got to the end, right? If we got to the end in our for each, right? So this is returning an iterator for us, then we know we didn't find it. If it's not equal to VN, then we can just say, hey, follow the iterator to what got returned from the for each. Okay. So let's see if we get lucky there. Okay. I got something wrong there. If I, thinking Python again. Sorry, folks. Too much context switching. There we go. Okay. So there was our answer, right? We found a 3, right? So somewhere in there was a 3. But if I put in like 21, right, we should get a not found, right? Not found. Okay. So again, the find if is returning an iterator if our little lambda found Q, right? By looking at each one individually, okay? So, and the lambda only exists for that moment in time and then it goes away, okay? So there's another kind of example of how you might use those things, okay? Like so. Ah, I knew I was supposed to do a modulo. Sorry, I did equivalent, but I should have done a modulo. Okay. So those are the kind of things that you would end up using that thing for. So for our lab today, it's really just a little data science. And this is probably really where you'd see this the most. It's like, hey, I need you for your internship to snarf up a million numbers and calculate some statistics. And why don't you use lambdas, you know? So that would be kind of what we're doing here today. So we're going to open and load the values. Now, for folks on program IZ, it will just be stored in a list container, so you don't have to open any files or anything. So it should be pretty easy. We use for each, like we did in our practice 6, to go through everything. And we want to compute and print out various statistics just using the for each and some inline transient lambdas. Okay, so just the way we've been doing it. We want to calculate the sum. So we just kind of did that a moment ago. The average. So you're going to probably need to use some references for that. And there's some hints in the code. The statistical variance. So this is not an equation that we all want to remember. So I have it here. It's the differences from the mean or the average. So you're going to have to pass in the previously computed average in the capture of your lambda for calculating the statistical variance. Okay, and there's some hints in there. And this is optional. But if you want to calculate the median with a lambda, it's pretty darn cool if you want to do that. But that's not a requirement for you. So that's just something else to chew on if people are interested in that. So let's take a quick look at the code and get you guys on to the next thing. So again, the Replit folks will have a file, but the code's already written for that part, right? So here's what we want to do. Real quick, get you set up. Here's our list, right? We will sort that list just for convenience. Remember that sort is a method of the list container. So nice. I think it's a quick sort. And then we will write our lambda right in here, okay? So this is all the lambda, okay? So start just as a warm-up, printing out each of the values, okay? And then try to compute the sum, okay? And now you have the sum up here, okay? So you can confirm it down here. And now you can pass the sum in to this one, right? For the next thing that you want to do. We're doing the computer total number size. Oh yeah, okay, and you've got the size, so you can use that to calculate the average. Anyway, I'll let you guys kind of figure that stuff out. But let me know if you have any questions. The median is the last thing. And otherwise, we'll see you on Tuesday. And let me know if you have questions. Oh, question. Yeah.
On that last function,
Yeah.
halfway is just listed as a variable, not a pointer.
Halfway. The variable is called halfway.
It's not passing in the address for it. It's just passing in halfway. The very last
Oh.
for each.
Oh, right. Okay, hold on. You mean here? Oh, halfway. Oh, okay. Previous mean. Yeah, it could be that you're not needing to change that.
Oh, okay.
Yeah, so the midpoint is probably what you need to know for the median, and that's probably the key piece of information. Good question though. Okay, so stick around if you have chess questions. Otherwise, I'll get everything graded as quickly as I can. Thanks everybody for all your hard work and the torture fest on the chess this week. So I think everybody's doing pretty good. All right, have a great weekend. We'll see you guys on Monday. Let me kill this for you.